Hi and hello to everyone. In this video, we are going to discuss about how to plot the spectrum of the amplitude modulated signal and a double sideband with suppressed carrier amplitude modulation. Okay. See, if I say amplitude modulation, the meaning is this can be also said as double sideband with carrier. Double sideband with carrier amplitude modulation. Okay. Or generally, I can simply say it's an amplitude modulated. Okay, and if I am going to suppress the carrier, that is I am going to suppress the carrier during modulation, then it is called double sideband with suppressed carrier. Okay, so if it is simply amplitude modulation, it is with carrier. I have to specifically mention the suppressed carrier. Clear? Welcome to the lecture. This is the first question. Draw the spectrum of the amplitude modulated. If I say amplitude modulated, the meaning is double sideband. That's particularly amplitude modulated double sideband suppressed carrier. Okay. So the question is 10 cos 2 pi 10 to the power 3t cos 2 pi 10 to the power 6t. Right. So how to proceed? See, before that we have to understand why this signal is an amplitude modulated signal. Right. For that we have to understand which is the carrier part. Okay, the higher frequency is the carrier frequency. We have two frequency components, 10 to the power 3, 10 to the power 6. So what is the highest frequency? 10 to the power 6. So your FC is, so this is the carrier frequency and this is the message frequency. Okay, and this is the message amplitude, I can say AM. Right? Okay. Now, after plotting that, you will understand why it is suppressed carrier. Okay, once you draw the spectrum, you will understand why we don't have the carrier at all in the after modulation. X of t is the modulated signal, right? So we know that this is cos A cos B, right? Cos A cos B can be written as cos A plus B plus cos A minus B by 2. Okay. So I can write this as cos A plus B. So it is 2 10 to the power 3 plus 10 to the power 6 plus cos A minus B 10 to the power 3 minus 10 to the power 6. Okay. So 10 to the power 3 plus 10 to the power 6 is 1001 into 10 to the power 3. 10 to the power 3 minus 10 to the power 6 is minus 999 into 10 to the power 3 frequency. And we very well know that cos signal is an even signal. Cos is an even signal. What do you mean by even signal? Which is cos of minus theta is cos theta. Right? Okay. Cos of minus theta is cos theta. So if you see the cosine signal, it is like this. Right. So you can see clearly the signal which is present in the positive time is same as the signal which is present at the negative time. Okay. So I can say if it is minus here, that minus is gone here. Right. Cos of minus theta is cos theta. Okay. Now before going into the plotting the spectrum, we should be able to we have to get the help from the Fourier transform, right? And we can recollect that what is the Fourier transform of 1, right? A constant. This is a time domain. Fourier transform relates time domain to frequency domain. Okay, time domain to frequency domain. In frequency domain, I can express in two ways. Either I can express in omega or I can express in f. And we very well know that omega is 2 pi f. Okay, right? If the unit of omega is radians per second, the unit of f is hertz. Okay, so interchangeably we should be able to apply based on our necessity. We can either express in Fourier transform in f or omega. So the Fourier transform of 1 is 2 pi del omega. 2 pi del omega. Okay, so how the spectrum will look like? 2 pi del omega means, so if you want to draw the spectrum, so this is my omega, right? Del omega. So omega should be 0, the amplitude is 2 pi. Okay. So at omega is 0, the amplitude is 2 pi. So this is the spectrum of the signal, time domain signal 1. Okay. Now I can express this instead of del omega, I can express this in f. Right. You can see this. Okay. You can use this as a reference. Okay. This will help you. Omega I can cite this as 2 pi f. Okay. And we very well know the relation delta of at. Delta of at is nothing but 1 by magnitude of a delta of t. Right. So in the same way, instead of t we have here f. Okay. So 2 pi is brought to the denominator and the 2 pi gets cancelled, is del f. Okay. So instead of saying 2 pi del omega in omega, I can say simply say the Fourier transform of 1 is del f. Okay, so I can plot the same spectrum by the axis f here. In this case, it is, this is the spectrum. This is the spectrum. Okay, right. So del omega, so you can clearly understand for 1, the Fourier transform is at the origin, that is del omega times 2 pi. So the impulse is at 2 pi. Impulse is at 0, whose magnitude is 2 pi. Similarly, the Fourier transform of 1, if you want to express in f, it is del f. Okay, now we'll understand what is the Fourier transform of e power j omega naught t. E power j omega naught t. This property is called frequency shifting property. Frequency shifting property. Frequency shifting property. Okay, what is frequency shifting property? It is e power j omega naught t, right? So it is, we have an exponential in time domain, there will be a shift in the frequency domain, right? Here in the exponential, what we have, in the exponential we have omega naught. In the exponential we have omega naught, right? Okay, so it is del of omega minus omega naught, right? Okay, so it's 2 pi del of, it is plus omega naught, so it is shifted by minus omega naught, right? This is expressing in terms of omega. So instead of that, I can express in f. If I expressing in f, it is del f minus f naught. Okay, next, if it is e power j minus j omega naught t, it becomes del of f plus f naught. Okay, so simply speaking, if you have an exponential term, e power j term in the time domain, there will be a shift in the frequency domain. F is shifted to f minus f naught. Here f is shifted to f plus f naught. Now with this help, we can write the Fourier transform of cos omega naught t. What is cos omega naught t? We very well know that it is e power j omega naught t plus e power minus j omega naught t by 2. Okay, we already found out what is the Fourier transform of e power j omega naught t is del f minus f naught. Okay, e power minus j omega naught t, it is del f plus f naught. Okay, divided by 2. Now we got an idea what is the Fourier transform of cos omega naught t, right? So we come back here, right? Okay, we come back here. What we have for the first term, it is del f minus f naught. What is f naught in this case? What is f naught in this case? 1001 into 10 to the power 3 plus del of f plus f naught. Okay, divided by 2. The 2 is here, right? Okay, for the second term, this is the Fourier transform divided by 2. The 2 I have commonly written here. Okay, right? Now we got an idea. So this is the spectrum. This is the Fourier transform of x of t. This is my x of t. Okay, now we can clearly say what are the frequencies present. Del of f minus 1001 into 10 to the power 3. So what value of f inside the bracket, it becomes 0. We know del 0 only exists. Okay, so f should be equal to, what is the frequency component? Okay, here it is 1001 into 10 to the power 3. Here it is minus 1001 into 10 to the power 3. Here it is 999 into minus 999 into 10 to the power 3. Here it is plus 999 into 10 to the power 3. Okay, so we have 4 frequency component and the amplitude is 5 divided by 2, which is 2.5. Okay, and you can clearly see the frequency components are for the first one. Okay, this is for the first one. Okay, and this is for this part. Okay, and this for this one, and this for this one. Okay, these are the frequency component, and the magnitude of them is 5 by 2, which is 2.5. And why it is a suppressed carrier? Okay, we said it's an amplitude modulated signal, but it is a suppressed carrier. Where suppressed carrier? We know what is the carrier frequency, 10 to the power 6. We don't have any component at 10 to the power 6. What is 10 to the 1000 into 10 to the power 3? Okay, see here I have written k. What is k? Is kilo, 10 to the power 3. Okay, we don't have any spectral component at which frequency? 10 to the no spectral component at 10 to the power 6, or I can say 1000 into 10 to the power 3 or 1000k. That is why this is called as suppressed carrier. Carrier is suppressed. So these are the carrier frequencies. Okay, 10 to the power 6. We don't have any component at 10 to the power 6. That is why this sort of modulation is called double sideband. Why it is called double sideband? We have the upper sideband. This is the upper sideband. This is the lower sideband. These are the lower sideband. Okay, these are the lower sideband. This is the upper sideband. Okay, right. So we have the upper sideband and lower sideband. We don't have any carrier component. That is why it is called as double sideband suppressed carrier. Next, this problem you can see here is a double sideband with the carrier, and it is a multi-tone amplitude modulated signal. Okay, if you see clearly, as I said, the highest frequency is the carrier frequency. Okay, what are the frequency component present? If you observe very closely, this is the first message signal. Okay, I can make a note here. Right, so this is the message signal. Let me put AM1. This is the 10 to the power 3 is message signal frequency 1, which is 10 to the power 3 hertz. What about this part? Okay, it's 2 pi f. Omega is 2 pi f. Okay, so here f is 2 into 10 to the power 3. Let me say this is FM2. Second message frequency is 2 into 10 to the power 3 hertz. What is the amplitude? AM2. AM2 is, in this case it is 10. Sorry, in this case it is 5. Okay, in this case it is 10. This is the carrier amplitude, which is 20. This is the carrier frequency, which is 10 to the power 6 hertz. Why it is called multi-tone? We have two message signals. First message signal frequency is 10 to the power 3. Second message signal frequency is 2 into 10 to the power 3. Okay, both the signals are modulated. What modulated? It's an amplitude modulator. If you can see the spectrum, you will understand why it is with the carrier. We don't suppress the carrier in this case. Okay, so further what we are going to do is we are just multiplying things inside. We are multiplying cos with the entire term. So it's 20 cos plus 10 cos 2 into 10 to the power 3 times cos 2 pi into 10 to the power 6 plus 5 cos 4 pi into 10 to the power 3 cos 2 pi into 10 to the power 6. Okay, so this is just I have done using I have multiplied. Okay, now we know from the previous question what is the spectrum of cos. We have just derived it, right? You can refer it, you can pause the video and you can make a note. Cos omega naught t, the spectrum is 1 by 2. Here the amplitude is 1. In this case the amplitude is 1, so it is 1 by 2 we are getting. Okay, 1 by 2 del of f minus f naught del plus del of f plus f naught. If you look at this case, here the amplitude is 20, so 20 divided by 2, so f naught in this case is f minus 10 power 6, so f minus 10 power 6 plus del of f plus 10 power 6. Okay, then what about this cos, if you think about it, cos a cos b, so it will be cos a plus b cos a minus b divided by 2. Okay, so we will get 10 divided by 2. Again we will write the exponential again divided by 2, so it is amplitude is 10 divided by 4 in this case. Okay, this is very similar to what we have done in the previous one. You can see here what we have here. Yeah, this part you see here, 10 cos a cos b. Okay, what is the answer you are getting? It's 5 by 2, which is 2.5, which is 10 divided by 4. Okay, 2.5 is 10 divided by 4. It's the same as this. Like, okay, this is same as this. So straight away writing the result, 10 divided by 4. So what is the frequency? 10 power 3 minus 10 power 6, 10 power 3 plus 10 power 6. Okay, then come to this part. What is amplitude here? 5. Okay, it is 5 cos a cos b, so it's 5 by 4. What is the frequency? 2 into 10 power 3 minus 10 power 6, 2 into 10 power 3 plus 10 power 6. Okay, we will get these frequencies. Okay, right. So now we got the spectrum. It's very well clear that what is the spectrum? This component exists only at 10 to the power 6. This exists only at minus 10 to the power 6. Okay, so in place of f, if I put 10 to the power 6, you will get del of 0. In place of f, if I put minus 10 to the power 6, I will get del of 0. Okay, so two components I have. 10 to the power 6 is nothing but 1000. So this is this component. No, sorry, not this one. This one. Okay, So this minus is this part. Similarly, what is amplitude? It is 20 by 2, which is 10. Here it is 10 by 4. What is the frequency? It is 999 into 10 power 3. Here it is minus 999 into 10 power 3. So your f should be, your f should be, your f should be 10 to the power 3. Your f should be minus 999 into 10 to the power 3. If you take this case, your f should be 998 into 10 to the power 3. Your f should be minus 998 into 10 to the power 3. Okay, right? So what are the component? 999 into 10 power 3, it's here. This component is here, and minus 999 into 10 power 3 is here. Okay, amplitude is 10 by 4 is 2.5. Here it is 5 by 4. 5 by 4 is 1.25. Where it exists? 998 into 10 to the power 3. 998 into 10 to the power 3 minus 998 10 power 3 is here. Okay. So now we would have understood why it is a double sideband with the carrier. Double sideband with the carrier. Because we have a separate carrier component. We have a separate carrier is present. As well as we have the upper sideband and lower sideband. Okay. We have the upper sideband and the lower sideband. Right. Got it. This is how we plot the spectrum. Okay. Right. Thanks for listening. Happy learning.